This is problem 16-27. A 20-pound slender rod AB shown in the figure is supported by a frictionless pin at A and a cord at B. If the cord at B breaks, determine the acceleration of the mass center of the bar and the reaction at support A in the instant that motion begins. All right, so in this problem, we're having to imagine that this line at B has broken, but the bar hasn't actually moved yet, but the acceleration has started. Okay, so sometimes that can be a little confusing. And if we look at how this structure is set up, you'll have a smooth pin at A, no friction, and the rod is only allowed to rotate about the axis Z at point A, meaning the rod's going to fall, okay? So there's only one new concept that is being added to this, but it is a very important concept that is a big deal. And if you look at the section of this book, you will see that it's not very long, but I'm going to show you how this math works and explain to you that we need to be adding in the rotational inertia of the object. So let's take a look at the math. If we start with the free body diagram of the object, we now want to draw our forces, and hopefully you remember this kind of analysis from CE 270, that we have a reaction force at pin A, both in the vertical and the horizontal. Okay, so I'll call this AY and AX. And then we are going to have a weight that is at the center of mass of the object. And they told us this is a 20-pound slender rod. Now, they say slender rod or slender bar specifically in the problem. That is a category for a particular shape, right? I will show you how important that word is in a minute. First of all, let's begin the analysis, because I'm going to tell you right away that this is a two-dimensional problem, just like in statics, and therefore you can do 3 equations per free body diagram for two-dimensional objects. For three-dimensional objects, you can do 6 equations per free body diagram. Now, the 3 equations that we can do here are some of the forces in the X, some of the forces in the Y, and some of the moments about some point. I'm going to choose A. So those are not the only 3 that we can do, but we can only do 3 equations. So don't forget that we're also allowed to do combinations like some of the forces, maybe about the center of gravity. You can pick anywhere. Sorry, I meant to say some moments about the center of gravity. And you are, however, only allowed to do 3 equations total. So one of these equations would have to go. Maybe it's some of the forces in the Y, or maybe it's some of the moments about A. You can only do 3 equations. All right, I'm going to choose the first 3 that I wrote, however. So now the setup is mostly the same thing that we have been dealing with so far. Our forces in the X are AX, that's it. And then we have the mass times acceleration on the other side, because this is Newton's law. Well, the mass is going to be the 20-pound weight divided by the acceleration due to gravity, that's mass, and then the acceleration of the center of gravity in the X direction. Some of the forces in the Y are going to be the AY minus 20 pounds, okay, equal to the 20 pounds divided by the acceleration due to gravity to calculate our mass, and then the acceleration of gravity in the Y direction. All right, I chose my positives to be up you can choose your positives to be down. So I am assuming that my acceleration in the y is going to be positive going up. The rod is about to fall. It is entirely allowed. I just wanted to show you this just once, just to say the positive direction is actually downward. So that would mean that the weight is 20 and the acceleration in the y is negative. And therefore now we can assume, sorry, the force AY is negative. And we can assume that the acceleration due to gravity is now going to be downward negative, because we know the object is going to go down. It's just a thing you're allowed to do. Next is some of the moments about A. All right, well, we have our reaction forces, AY and AX, actually located at A, so there are no distances from A for those forces. The only force that has a perpendicular distance from A is the 20-pound center of gravity. Okay, that means that we have a rod that is 36 inches long, which is the same as 3 feet. And so halfway is where the 20-pound weight is. That means that we will have a 1.5-foot distance with a 20-pound force, and that is our moment created by the 20-pound center of gravity. And this is where things change. In statics, we would just be equal to 0 because nothing was moving. Now we have rotation. So we have two terms here. We have the rotational inertia about point A, and then we have the angular acceleration. Now you can think of this as kind of like the mass times acceleration in Newton's law. The rotational acceleration is basically the rotational inertia is the mass term, the inertial term for spinning. Okay, so the M in the F equals ma is how much resistance to motion the object has. The I in the rotational inertia is the resistance to spinning. Okay, and then we have our alpha, which is the acceleration term, like in F equals ma, but it's for the spinning acceleration. So it's the same idea, just that we're talking about rotation instead of translation. So how many unknowns do we have? Well, we have AY, AX, AGX, AGY, inertia, alpha. That's like 6 unknowns. Okay, so we've got a problem. Now, how do we get 3 more equations? Because we have 3 equations, 6 unknowns. Well, we know that this rod is about to spin. And it's about to spin and go in the downward direction. So if we basically do a relative acceleration diagram, like we've done in the past, then we can have point A and point B, all right? And we can also, since we have, if this is a relative acceleration diagram, and we have accelerations, let me erase my circles because I'm going to make new circles. We have an acceleration here and here. All right, but where is acceleration AGX and AGY? Actually, it's in the middle of the rod. So my diagram isn't exactly appropriate for finding extra terms that I already have in my first 3 equations. What I want to do is, let's erase, label this G, and my relative acceleration diagram will only go to G. Then I have my tangential and normal acceleration here. Okay, so B is floating out to the right. And let me label these. So this is AGY, and this is AGX. Or it's the acceleration of the tangential, and the acceleration in the normal. All right, well, what were the terms? Well, acceleration in the tangential is the radius times alpha, and the acceleration in the normal is the radius times omega squared. All right, if the center of gravity is halfway, just like we had calculated for the 20 pounds, then the radius is 1.5. 1.5. And what is the alpha? Well, we actually don't know. But that alpha is not an additional unknown. And then here, for the normal, if we have 1.5 as the radius, do we know the omega squared? Well, we do, because the problem says that the motion is beginning, but I clarified that the motion hasn't started. So therefore, the rotation hasn't actually begun yet. So that means that the omega is 0. So omega is not an unknown. And therefore, we know that the acceleration of g in the x is 0. Okay, good to go, 0. What about acceleration in the y? Well, we don't know the number, but at least we know that we can rewrite the 20, 32 over 2, and we can rewrite AGY as 1.5 times alpha. So we've gotten rid of an unknown. We've turned the acceleration of gravity in the y direction into a term in alpha. All right, so now we only have 4 unknowns. Next is the new issue to deal with. We can actually calculate what this rotational inertia about A is. Now, if we look at page 620 of the textbook, we'll see that there is a chart. And that chart is showing us a bunch of three-dimensional objects, and they have labels. So the first object in the chart is called slender rod. Take a look at that. And what you'll see is they have a 3D axis, y, x, and z, and then they have a rod drawn on the axis, and they say that the center of gravity is in the middle of the rod, G, but they place the center of gravity of the rod at the origin. And what they are implying is that this object is going to rotate about this point G, which means there's an equal amount of rod in front of G and behind G. And they say that the length of this rod is basically L. But they have L over 2 on one side and L over 2 on the other. All right, so that is the diagram. Then they give us some terms. So they say I sub x is equal to 0. And then they say I sub y is equal to I sub z, which is equal to 1/2 ml squared. All right, I'll tell you now that there is a way to calculate this 1/2 ml squared by hand using calculus. I'm not going to worry about that. You've got enough to deal with in this course. You can just, for now, be using the values that are given in this chart. So refer to this chart for different shapes. You'll primarily be using the shapes on page 620. You'll very rarely use the shapes on 621, but for the sphere, don't completely ignore. And I think there's even a couple problems that might use the circular cylinder or the hemisphere, but primarily you're going to have the thin circular plate, the thin rectangular plate, the slender rod. And just keep in mind that even though page 620 shows you three-dimensional objects, you can treat these objects like two-dimensional objects, and you only care about the rotational axis about z, essentially. Well, why is that? Because you can consider z to be coming out of your paper or out of the screen. and then look at the object straight on from axis Z. And basically, that is what this problem is. That you have this three-dimensional object that's only allowed to be viewed and only allowed to move in a two-dimensional plane. All right, so they're calling it a slender rod in the problem, or slender bar. And so that's the thing. They call it a slender bar in the problem, but they call it a slender rod in the table. Don't read too deeply into that. Same thing. Okay, it's unfortunate that they don't be consistent with their terminology. All right, so real quick, how is the rotational inertia determined? Well, that was with the calculus math, but also how do you interpret this information? So imagine I sub y is rotating the object, and this is a little difficult for me to portray in 3D space on a 2D screen without you being able to see me wave my hands around, but imagine that the rod is rotating about the y-axis. So it's kind of like it's spinning on the table, right? The inertia, the rotational inertia about the z is, like I was saying before, we're looking at the object from the screen, looking at it from the side, and the object is rotating within the plane of the screen, right? Which is basically the viewpoint that the problem is giving us. Now, what about x? Why is rotational inertia about x0? Well, that is because the rod is slender, okay? It has thickness, but we're saying that the thickness is so small that it is practically negligible. So the object rotating about the x-axis will have practically no inertia compared to whatever is happening, whatever else is happening in the problem. This is kind of one of these things in engineering where the close enough moment. When I teach face-to-face, I've never said it in the videos, that engineering is the practice of close enough. And that's kind of my silly joking way of saying that engineering, of course, like if you're talking about an airplane or a car where we care about safety systems, close enough is, well, not the kind of term you usually throw around when you're talking about people's lives, but you're never perfect. So what do? We over-engineer the car and the plane to make it overly safe. And overly safe is the mark we want, and we try to get close enough to that mark to be like, okay, we're good to go. Okay, and close enough in this case is like, for airplanes, like a safety factor of like 5 or 10 or something. It's like planes are ridiculously over-engineered. But if you consider that goal of over-engineering the plane to be where you need to be, then when you get close enough to say we're within the margin of error, then that's what I mean. And so sometimes you can ignore certain characteristics. And since this is called a slender rod, we're imagining the rod is so long but so thin that rotating about the x practically has zero inertia. Okay, now that I've really destroyed that idea here, let's go back to the problem, because this table that I have been showing you, this guy right here, is for the rotational acceleration about point G. But in the problem, I am not calculating a moment about G, and I do not have a rotational acceleration about G. I have about A. I'm over here at A. So since the table, it's not specifically saying this, but just want you to know that this is actually I sub G in the X, in the Y, and in the Z. This is I sub A in the problem. It's different. So there's a little extra piece of information that's required. And the books section doesn't really go into it, but in the example problems for this section, it shows. So if you go to page 272, check that page out, and look, at the beginning of the solution section, they have what I've written. some of the forces in the x, some of the forces in the y, and some of the moments about A. They have I sub A times alpha. All right, this is equation A, B, and C on page 272. Now, look at how they handle the IA of Z. They continue on underneath the equation A, B, and C and say it's equal to the rotational inertia of G in the Z direction, okay, plus the mass times D squared. Okay, well, the I sub G term ends up being, let me make some space. The I sub G term ends up being 1/12 ml squared. Okay, that is familiar. That is the slender rod equation of the chapter. And then they have this plus ml over 2 squared. What is this? This is shifting our rotational inertia away from G to another location. The location is whatever the distance is from G. All right, so that's what this D is. Well, what in the example on page 272 is D equal to? It's equal to half the length of the rod. All right, then they finish adding in the values. So try not to get too distracted here. They do the 1/12. The mass of the rod in their problem is 10 kilograms. And then the length of the rod is 1 meter. Okay, so then they have 1 squared. All right, then they say plus the md squared, which is the 10 kilograms times a distance from G of 0.5 meters. So that's where the 0.5 is coming from. And then they're squaring. All right, so that's how we calculate the rotational inertia of an object rotating at a point that isn't at the center of gravity. We take the rotational inertia that's given to us in the table at the center of gravity, and we do this shifting term by the distance that we want to shift. And we have to take into consideration the mass of the object. All right, so with that, let's apply it. Let's erase these, and let's apply this concept to our problem that we are actually doing. All right? We have, again, a slender rod. So still the same thing, 1/12, and then the mass times the length squared. And then plus the md squared. Again, I'll just write it. Okay, now 1/12, what is the mass of our object? Well, it's the 20 pounds divided by the acceleration due to gravity. And then what is the length of our object? The length is the 3 feet squared. Okay, and then now we have to do the shift. So we will do 20 pounds divided by 32.2. And then the shift is going to be half the length of the rod. So 1.5 feet squared. Okay, so what that ends up doing is that ends up adding up those two terms to equal basically 1/3 times 20 over 32.2 times 3 squared. I know this might be a weird way for me to write this, but check it out. Now we have a value for the rotational inertia about point A. Okay, so if we recap, we ended up with 6 unknowns, but acceleration of G in the X is 0, acceleration of G in the Y could be written in terms of rotational inertia. And we just found the value for the rotational inertia of A. And sorry, I meant that the acceleration of G in the Y is the angular acceleration. Okay, so now we have 4 equations and only 4 unknowns. So we can solve. What are the answers? We have alpha equal to 16.1 radians per second squared. We have a sub gy equal to 24.2 feet per second squared, and it happens to be going downward. And if you get a positive answer, we had set down to be positive for some of the forces in the y. Not because you have to always do it that way. I just wanted to show you that that is allowed. We have the AX force equal to 0 pounds, and we have the AY force equal to 5 pounds.